But share. Okay, so let's dive into the big data topic, which is a pretty fun topic to discuss. And what's fun about big data in particular is that it's something that really does require some specialized tools and some specialized knowledge, and that's what we're going to discuss, or what are the cloud-based tools that will allow you to deal with big data, and then also even what is big data. And I think a good place to start is the definition. So people talk about big data all the time, but well, what do they mean by it? One of the best definitions I've ever heard is this 3Vs concept. So the 3Vs concept is you've got variety, you've got velocity, and then you also have volume. And what I like about that is it does really encapsulate some of the things that happen with big data. And if we look at, for example, a big data type system, which is now really the center of the universe, which is a data lake. With a data lake, it can handle all of those things at the same time. And the reason why it can handle all these things at the same time is that the data lake has that concept of the infinite disk I/O. It has the concept of, infinite storage. It can go up as much as you want, and then also the velocity concept is something that a data lake can handle. So let's just think about S3 in particular. What's nice about it is that it can take streaming data, and it can also take the batch data. And what this means is that in the old days, if you had to build some kind of a pipeline or process things with a cluster of machines like spot instances or something like that, you would have to build these really specialized tools. But in the case of a data lake, the instances can automatically get high-speed network access to it, and specialized tools will know how to use it. So what are some of these specialized tools? One of them is the classic EMR system on Amazon, and it stands for Elastic Map Reduce. And Amazon has a habit of building these specialized names for tools that are really open source projects. So what is EMR? The most modern variant of EMR is Spark, which is built on top of Hadoop. And that's what a lot of people are doing in terms of using big data tools. If they need to, let's say, provision, 20 nodes to do clustering or something like that, and they have some existing Spark code, this EMR system would work really well with the Amazon platform. Likewise, Google would be a good platform for doing their version of this using Managed Spark, and then Azure has the same version as well. So a lot of times what you'll notice is that I would say the most predominant tool that people are going to use on a data lake right now would be things like Spark and Hadoop. But I would call that really like a Gen 1 tool. And it's just like how there was, CGI websites, how there's old school websites, and then there's Web 2.0, which was JavaScript and asynchronous coding and all this stuff. It's a bit the same way, where the first version of big data, a lot of times people are using these tools that really had origins even before the cloud era, the Hadoop system. But let's talk about some cloud native big data tools. And I think this is where a lot of the really exciting stuff is happening. So what are some cloud native big data tools? One of the cloud native big data tools is this whole ML ecosystem. And what we have seen in terms of cloud native big data is that, again, our friend the data lake is back. But this time it's a little bit different in that the tools know implicitly how to handle talking to something like Amazon S3. And in fact, the entire system itself is designed to deal with this. And so that's really what something like SageMaker does, is it's a next generation cloud native tool that is a ML platform. And I think this is really what we're going to be seeing over the next few years here, is that the cloud native, which we'll call generation 2, will really be able to take advantage of things like what we covered last week, which is it'll be able to take advantage of serverless technologies. It'll be able to take advantage of, for example, Glue systems, so AWS Glue, which is a data warehousing tool that can index things. Things like Athena, which can do serverless queries. So I think, what are some of the characteristics of a Generation 2 big data system? I would say that they know how to use the object storage system. So that's one characteristic. They also are built in a cloud native way, which we'll just call this CN. They also have serverless as really the primary or even preferred method of dealing with things. And also they're designed around cloud platforms. And so the cloud platform itself will have hooks that will do, even though it's cloud native, it's also designed to have like proprietary types of technologies where these cloud providers want to get you deeper into their ecosystem. So it's just something to think about when you're thinking about big data, is that there are really a couple different generations of big data, in my opinion. There's the old big data, which are things like Hadoop and Spark, and there's nothing wrong with them. Or Databricks is another example of that. And then there's the new generation of cloud native big data, and typically they involve these things like SageMaker, AWS, Athena, also tools like on the Google Cloud Platform. They have managed big data systems involving serverless technology, and then also Azure as well. So there's this new serverless data engineering pipeline. So what I was going to cover next year is I'm going to go through a lab that goes through some big data stuff on the AWS platform. So what I'll do is go to my Vocarium account here, and I'm going to go to a big data lab that should have some interesting stuff for me. So I'm going to log in and go to this account, and I'm going to go to a data analytics account. And this is something that's available as kind of a next generation after you pass the solutions architect or cloud data or the cloud practitioner exam. If you're going to study for, let's say, the big data or data analytics exam, this would be the kind of labs that you would go through. And one of the ones in particular that I wanted to cover was walking through this lab, which is query data and Amazon with Amazon Athena and Glue. So I'm going to open up another tab in another window so I can kind of navigate myself through this. But what we're going to do here is we're going to practice using the AWS Management Console to create crawler tables in a schema with Glue. And then we'll also query the S3 system from Athena and the AWS Glue catalog. So this is really a pretty good example of like what you would do if you were hired as a data engineer at a company and they wanted you to build a modern data engineering pipeline. This would be probably one of the first stops in your journey. So let's go through and take a look at this project. So I'm going to just click Start Lab because it usually takes a little bit of time to spin up these big data labs here. But basically, I'm going to go through here and just walk through the exercise. Big data problems often involve a large number of heterogeneous data sources. As a data analyst, you might know that you may not know the schema for some data sources. So this is really common as well if you're working with medical data or biology data or something. And this is a variety of the 5 datas, right? The 5 V's. I only talked about 3. They have a few more here, which is volume, variety, velocity, veracity, and value. In this lab, we're going to work with glue, and what glue does is it attaches to a data source, and it can actually automatically figure out what the schema is based on the data types that it discovers. And then glue will build a catalog that contains the metadata about various sources. And then once you have that catalog, that's really the first step to doing a big data operation, because the Athena service can query the index. So it doesn't have to actually pull out petabytes of data to go through and pull things out. So this is really a critical step, is can you index the data before you do some big data operations, so that you don't have this gigantic bunch of data that you're pulling in and out. So what does glue integrate? Well, it can integrate with Athena, which we'll use to query it. It can also integrate with Redshift, which is a data warehouse that Amazon has that's a competitor to, let's say, Oracle. And then Amazon EMR, which we talked about earlier, which is a kind of a generation 1 big data system. So after this lab is complete, you're going to be able to look at AWS Glue in the management console, create a crawler with AWS Glue, create tables and a schema with Glue, and then also query data that lives in S3 from Athena by using that catalog that we create. So what are the prereqs here? These are typical prereqs. Is just basically you have to have a computer that works. And so we went through and we clicked Start Lab here. And the next step is I'm going to walk you through this scenario here. So in this scenario, you're a data analyst who works for an international development agency. This agency focuses on drought relief, and you're asked to look for weather patterns since 1950. And this kind of a lab really is very realistic. And this is something that I would say at a data science program I teach at some university, this would be probably very similar to some question a student would have or a researcher would have. And so fortunately for you, the global weather data is already stored in S3. So this is a plus. If your data is already in S3, then it does make the problem a little easier. The National Centers for Environmental Information, NCEI, which is in the US, maintains a data set of climate data. This data set includes observations from weather stations around the globe. And the Global Historical Climatology Network Daily, or GHCND, contains daily weather summaries from ground-based stations. The dataset contains data that goes back to 1763, and it's updated daily. So the most common recorded parameters are daily temperatures, rainfall, snowfall. These parameters are useful for assessing risks like drought, flooding, and extreme weather. And the data definitions themselves are actually available on the AWS Open Data website. So this is another just call out here to look at, is that AWS has these open data sets here. And I know this is something that a lot of students want to know about, is how do I get access to open data sets? And this is shows you exactly how to use it, how to query it from your Amazon account using some of the things that we've already covered previously, like Cloud9, for example. If I spun up a Cloud9 instance, I could immediately use this, right? I could actually pull this into Cloud9, or if I wanted to pull it into SageMaker, and then this goes through the schema and kind of tells you all the different things about this. So here's the architectural diagram, and this is really critical for, if you're in the real world, and let's say you're hired as a data engineer at a company or data engineer at a university, I think this is a very good idea to draw something like this first, to make sure that you know what you're building, and also to explain to people, because the complexity of building a big data solution is much higher than if you're just kind of willy-nilly going through and building like a serverless Python function or something. There's a lot of stuff happening here, and it's important to use to use an expression, measure twice and cut once. You want to make sure that you're thoughtful about spending a lot of money. So task 1 would be to create a crawler for this data set using that for the GHCN data set that's already on Amazon. And again, as a data analyst or scientist, you may not be aware of the scheme of the data. And this is very, very common. In fact, this is one of the most common things that I've found, is that you have no idea what's happening. You have some data that you need to do something with, and glue is really optimal for this. And this is going to be a fun demo to show you. So we can access, yes, sure. Yeah. Yeah, it's a good question. So typically in a diagram like this would be a bidirectional feedback loop. So in the case of the IM system here, because you're going to be changing and adding roles and going back and forth, there's a kind of back and forth. In the case of the IM user, you're going to be, I believe, just accessing the data in one direction. And then in terms of the Athena diagram here, because glue is going to be frequently going back and forth, there would be a bidirectional workflow. Now, one thing I will say as well is that a human drew one of these diagrams, and it's up to interpretation whether how bidirectional it really should be or not, and how careful they were. I don't think there's any hard and fast rule about when you should make an arrow that points both ways or another. It's slightly up to artistic interpretation. I think the one that does make a lot of sense to me is that the AWS Glue and Athena are going to be going back and forth and kind of communicating with each other. But yeah, it may be hard to definitively at this level of a diagram, completely interpret the directional nature of it. But I don't think it's a bad idea to, when you're drawing a diagram, is to maybe make it clear, and even you could put a little bit of a like a line annotation here that tells what is the nature of the communication. But yeah, I think in this one, it's tough to definitively say that the bidirectional nature is communicating something because of how simple it is. But I could see a scenario where it would be a good idea to be really explicit about it, and maybe even you could put a legend, on the side that says, these are the resources that talk to each other. There is actually a really interesting, kind of on that note, there's an interesting tool called what is it? AWS diagrams or something like that. There's I just saw this recently, and AWS diagrams, GitHub, and yeah, this thing. So if you're curious about maybe a proper way to draw diagrams as code, and even just, I don't know if I had shown this before, but this is kind of a neat little tool here. It's called Mini Grammar, and I think in this case it would be really actually a directional based diagram. And I think there's some examples here where, let's see here, I was just looking at one of these recently where they talked about some kind of detailed workflows where they show one thing is pointing to another thing. Like, for example, AWS, let's see, diagrams, clusters. Yeah, so like, for example, here's one that you could look at where you would see that the DNS server would create this database, it would connect to this database service, and then in this case, this is kind of called out into its own cluster, and then the cluster is separated by this. So maybe the short answer would be something like this might be the way to, if you want to get really down to the details and make it very clear about your diagram. I kind of like this tool, and especially because you can actually check this into your project, and you could have your project documentation also as source code. So very, very long answer. Hopefully that was helpful. Okay. So what we're going to do here is I'm going to maybe what's a little bit tricky about this is that because you can't see both of these, maybe what I could do is I could just do this. We'll give this a go, and I'll try to have two of them at the same time here, and see if we can both launch the lab, which is here. Yeah, I think I can do this. I can if I can do it if it doesn't kick me out. Failed to launch the AWS console. That's weird. Let's double check here. Let's try one more time. So end lab. Let's try it one more time here. Okay. Yeah, let me just see if I can get this thing started one more time. I'm not sure. This account is, oh jeez. This thing, the downside of this kind of this complex of a lab is that occasionally they have issues. So, but what I can do is, let me do this. I'm going to just do this. There's a simpler version of this lab that I can go to that won't be, hopefully will not have as much issue, and maybe is even easier to explain. So this is just a very basic Athena query lab, and I will look at this. It's the difference here is that, well, first of all, let me just start this and make sure it doesn't blow up. And hopefully there's no issues with it. But basically this one will be a little bit different. You're a data analyst. You're going to go through here, and it looks like it's in creation status. So that's good. And I believe will be able to give you all access to the advanced labs. I'm working out some of the details here, but okay, this in theory this lab says ready, and if I click on AWS, it lets me in. Okay, so that's good. So we got at least one of them running here. So let me kind of switch gears to I'll just kind of go back and forth here with these two labs. So this one is just a little bit easier. It's similar, but this one is just going to query Athena, and it's not going to use glue at all. And so it might be even a little bit easier to explain. And so basically Athena is going to create tables and define data types, and it's going to query data in S3. And the scenario is your data analyst and your manager wants to look for customer usage, and you want to minimize the cost, which is something that Athena would do. So this one's actually, again, a lot simpler, so maybe it was better. Destiny is letting us use the simpler version. Is all I'm going to do is just use Athena to query S3. And so how I'm going to do this, we're going to write a query that shows the data in S3, and you can actually store the queries for reuse. So that's another thing that's pretty neat about something like Athena, is that you can save copies of it and store it again. So let's say that you created a query that was show me all the high paying customers, then that would be something that you could pull up whenever you wanted to. And so these are just the steps that we're going to go through to actually do this. So I'm going to just kind of go through here step by step. So task one is create and query an Athena database. Okay, so let's kind of keep this to the side. I think that's decent, right? So I can go here and I can go to Athena. So let's type in Athena here. Query data in S3 using SQL. Okay, get started. And let's see here. It says first task is to go to services, click on get started, and it will go through a tutorial, but we want to close the tutorial here. So we don't want to do the tutorial. To close the tutorial window. So let's go back to Athena. I'm not sure why this tutorial window is waking up here, but and then the next thing that we're going to do, before you run the query, set up a query location. So connect your data source, query data in S3. So basically, we're going to go to services and choose S3. And again, management console services, choose S3, a bucket. So we're going to go to, and I think I'll just open up another window here. It's a little bit hard to kind of toggle back and forth here, but maybe I'll keep another copy of it to the side where you can't see it, so it's a little bit easier for me to just look ahead and not have to toggle back and forth as much. Okay, so I'm going to go to S3 here, and I'm going to next up find a bucket, and there should just be one bucket that was created for us. And we're going to go to the properties, I believe, and we're going to, I think we just go to, there's a section here where we can copy the, is it access points, management? Where's this thing? There should be a section here where I can copy the URL to the bucket. I don't know why this is escaping me. And the bucket property window, choose bucket. Where is this bucket property window? Maybe it's just so small and I'm just missing it. I'm just going to make this a little bit tinier for a second. So I see properties. Or is it, if I select on this maybe, there we go, copy bucket. It was just hidden there. Okay, so so basically what I did is I went to the bucket, I clicked on it, or I selected it. That's what happened. It's just the UI is really clumsy. And I click on copy bucket ARN. So this just gives me the full resource ID for that. Then I'm going to go back to Athena here, and I'm going to set up a query result location in S3. So what I will do is, let's go back to Athena, get started here, and I believe I would have to just say connect a data source, query a data result location, and is S3 located here? Choose an existing catalog. Maybe this will work. Why am I missing this? This is tab tutorial. You'll see the following message at the top of your console. So let's go back here, get started. Or actually, let me go one more time, sorry. So if I go here, we're going to do query data, get started. So maybe it's just under query data, data sources, connect data source. Yeah, it looks a little bit weird. Let me just see what this does. No, it's not it. For some reason, this is escaping me. I'll show you what I'm struggling with. So this one, I don't know if they changed the console or not, but we're going to specify an Amazon Simple Storage Service bucket to hold the results. We're going to go to the services menu. We did that, we copied it. Then we're going to go back to Athena and go to services menu, choose Athena, and it says set up a query result in S3, which is not an option. They may have changed the user interface. So I believe though, oh, there we go. So that's what I'm missing. So I just didn't read the UI. They tweaked the UI. So if you see here, before you run your first query, you just set up a query result location. Okay, we got that. And then I can paste in the ARN here. And the name of the bucket is the long string at the end of the bucket ARN. Before the name of the bucket, make sure you put S3 and terminate with a slash as shown. So they show like that. Okay, so we're going to go ahead and do that. So we see that the bucket name would be this part, and I'll make this a little bit bigger. This might be hard for people to read. So I'm going to say S3 like that, and then at the end of it, I'm going to put this slash. And so just to show you the match here, if you look at the name of the bucket, you can see that. Let's just go, I guess that's the lowest level. It's kind of hard to see, but basically the bucket, the name itself is this. This is the bucket. So it's kind of a weird name. It's not that common that you would have a bucket that's that big, but in our case, it is that big. And I'm going to go ahead and say save. Okay. Next up, I'm going to say in the editor, I'm going to say create database taxi data. So let's go ahead and close all this stuff. In fact, these queries are already in here, so I'm gonna make it a little harder for myself. So I'm gonna say create database called taxi data. So let's go ahead and go through here and say run query. So this should be here. Save or format query. Save as, and we'll say query taxi. Let's try this. Q. So let's go ahead and run this. And now that I've got this, you can see that it was able to successfully create this Athena database. So the next step, we kind of got through the hardest part, I think, is the initial setup here, is we're going to, in the table name box, we want to go, I guess, go here and go to basically go to the table name box here. So select taxi from the drop-down list of databases. So let's make sure. So we call the database taxi data, and then we're going to put in the table name. We want to enter. Let's just double check here. Enter yellow. Choose create data. Oh, create table, and then choose from S3 bucket. So let's go ahead and say create table from S3 bucket. And then we'll say in the table name, select yellow. So let's go through here. And I think we want to say, choose this, which would be select taxi from the drop-down list, and we'll call this one yellow, like that. And then the location of the input set would be this, just like that. Okay, so we created a database that refers to that S3 bucket, and we're going to create this new table name. And then the next thing that we will do is choose next, data format, select CSV, next, bulk add columns, and then we're going to add this code in here. Okay, so we're going to say go next. We're going to say CSV, and we're going to say next, and then we're going to say bulk add columns, and then from here I'm going to put a bunch of SQL schema data inside. and this will basically lay down the foundation of our schema. So it's going to say vendor string, pickup, count. These are just the definition of the attributes inside of here. So hopefully that cut and paste works okay. You never know. And look, it went through and it identified all these columns. And then the next thing, so I'm going to scroll down to the bottom here, is I'm going to go to next. And then if you notice here, after we go through it, it says create table. And Athena creates a table, and you'll see the following. So it's going to basically create this table with this schema information. So we'll go ahead and say create table. Okay, that looks like it did do that. And if we look through here, the table property indicates that the data is not encrypted. And this is a data serialization format. And this format requires comma delimited information. And now that we have this, we can query the AnyCab company. And so how would we do this? We would say from the list, choose database, choose the vertical ellipsis, and then choose preview table. So if I go through here, I can click on preview table. And then I believe, there we go. So we can see that it's got some data in there. So a little bit clumsy. I was not smooth at doing that, but what now we're able to actually do previews of this big data that's stored in S3, which is pretty cool. So we can essentially treat S3 like a relational database, which if you have big data is quite powerful. Okay, so what are we going to do next here? We're going to optimize the database. So this Athena query engine is based on an open source tool called Presto. So this is another thing just to point out about all of these big data tools is that on AWS in particular, is they name everything something different. So in their case, Presto is actually the open source tool, but they call it Athena. And so if you want to read more about how to do SQL functions with Athena, you can read SQL queries, and there's a whole documentation. And in fact, let's just look at it real quick. And you can see the kind of things you could do, like a select, an insert, and you know what's kind of cool about this is just imagine if you were able to get your data, you had petabytes of data that were, I don't know, DNA sequencing data or some kind of crazy bit of information, and you're able to actually use that a SQL query without having to move all the data around or change it around. You could just do a few commands here and query it. So that's really the power of something like this. And so in this task, we're going to compare the query time and the amount of data that's scanned, because that's how you're going to get charged for two different ways of loading the data into Athena. So the first one would be, we'll create a table that contains all of the taxi data for the year 2017. Then we'll create a table that contains the data for a single month. So we're going to be able to compare the processing time from a year's worth of data, and then also look at the processing time for a month's worth of data, which is actually a very useful exercise to know how to do. And so this is one of the goals that hopefully you'll be able to learn by the end of this, is that when you do have a large data set, can you tweak the tables so that maybe you only query the things frequently that you need. And so Athena here is going to give different pricing based on the different usage patterns. And this is how the BigQuery system works for Google. And if we have time, we can also do a BigQuery tutorial as well. So let's also mention that this is another thing that happens a lot with big data, is partitioning and compressing the data are two steps that you can take to minimize costs. And this starts to get into some really tricky things that really could save a lot of money, is can you compress your data here? And so how are we going to do this? Well, we can improve the performance when you query with Athena by storing the data in distinct buckets. Okay, so let's go ahead and do this. So what we're going to do again is we're going to create two different kinds of time-based buckets. One will have a year worth of data, and one will have a month worth of data, which is also a very common operation I could see somebody doing. So first step, we're going to create a table for 2017. So we'll say new query, and we're going to run this query. So let's go to new query here, like this. And then we're going to say run query, and we're going to paste this code in, right? And always a scary thing to do, to just blindly cut and paste code from the internet. Hopefully, though, in this case, it's not completely the internet, because it's our friends at AWS. Oh, so irritating that they make it difficult to copy and paste this. I think I'm going to temporarily go like this and just make this like super tiny, and then put it on one line here. So we're going to do this, and there we go. So this is January 2017, and I'll just throw this in there. And we can, and I think this is not a bad idea if they have tools like this to format it so you can actually read what's going on. And it's going to create this table if it doesn't exist. And it's also going to use this data format here with some special properties like field delimiting. And it's going to grab it, I believe, from this location right here. And then also we see that it says it's not encrypted. So let's go ahead and run that. And, or no, save. Actually, I don't think we have to save it. I think we just run it. Well, oh, what is it? What is it saying here? I think I pasted something bad. Oh yeah, mismatched row. So I need to actually fix that. Let's go ahead and copy and paste this again. Hopefully there's not some kind of bad problem with their query that they gave us, which happens. I'm just going to copy here and paste this in. Hopefully they don't give us a bad query. Okay, so when I formatted it, I must have screwed something up. So this creates a new table called January, and we could do the same thing we did before, right? If I go to January, I can now preview the table, which is not a bad way to kind of see what's going on here. And in fact, you can see the different preview data, and I could even do things like sort and all kinds of fun stuff. And I think I can even do this. When I say preview, I thought that there was a way. Yeah, so basically it's all a preview does is just generate a like a kind of a sample query for you. So if you wanted to, you could actually make this bigger, right? So we could go through here and we could run our own query and just really hammer it because we're not paying for it. And you can see that this one's got more data, and then I could sort by all 1,000 records here, and I could look at everything that's happening. So this is probably a good tool to use as this like preview tool here. So next up, we're going to run a query using the data that's not divided into buckets. So we're going to again run this query, and we're going to note how much data is scanned here. So I'm going to make a new query. I'm just going to close this one and go here, make a new query window, paste this in. And so what this is going to do is going to count the number of trips, and it's going to say from basically the timestamp of 2018 March 1 to 2018 February 1. So let's go ahead and run it. And this thing is going to take a little bit of time. It's taking several seconds actually. So it queried 9 gigs of data. So this could add up. If you start querying 10, I mean, if you see though how powerful this is too, imagine on your local laptop scanning 9 gigs of data and doing something to it. I mean, that's a lot of data. And it only did it in 5 seconds. And also we can tweak the query. So that's the first query. Now let's run a query using the data that's divided into buckets for each month. And let's just double check here. Did we? Let's go through it. Let's look at this query. And let's do another one. And so this is going to say from January group by pickup. Kind of interesting that this took longer. It took 11 seconds, but it only scanned 815 megabytes of data. So if we look at what they're telling you, is that with no buckets, the data scanned was 9 gigs, but when you use a bucket, so basically you can optimize your query to not have to search as much data. So if we put the data in separate buckets, this is going to work when you have data that's got a high degree of cardinality. So this refers to the distinct records in the database. In this case, the pickup field has a high degree because of the specific date and time. And then in some cases, your data will be partitioned by another process. So you can see here, these are the pay type field. So because there's only a limited number of possible value types, pay type is an excellent column to use for creating partitions. And in this task, you're going to create table as function to partition the data. And this is going to specify a columnar data store format. So you can store this with Athena with either the Parquet format or the ORC format. And these columnar formats are a way of basically compressing the data and also making them suited to doing distributed queries. So let's go ahead and partition this data. I'm going to go through here. I'm going to make a query called create table. So let's go ahead and do this. I'm going to paste this in here. And this is going to create a new table called taxi data credit card in the Parquet format. And while that's working, okay, so that was able to be successful, and you can see it's right there. And now that we've got that, what we can do next is we can actually start to query that new table. So what I'm going to do is I'm going to run this one. So we're going to run this first one, which is sum up the pay type data here. So select sum pay type from yellow, where pay type 1. So basically, if I look at this credit card, yellow, and then pay type here, you can see you can check out the schema and see which things I could possibly query. But let's go ahead and run this first one. And this one will be able to run probably like 7 seconds or something like that, with maybe 9 gigs or so of data, maybe more. Okay. And so it was 19 seconds with, it scanned though 9 gigs of data. And then the next one will be this one. And this one in theory should be much smaller, only 71 meg. So I'm going to create another query, go here. So in this case, we're going to say group by a pay type. And I guess the idea here is that when you have partitioned data, in this case, the non-partitioned data is in the yellow table, and the partitioned data is in the credit card table. And so the end result is that you can see I went from, on one hand, running something that was like 9 gigs that I queried to, in this example, 71 megabytes, right? So huge difference here in terms of, when you're able to partition the data and kind of move it around. So this could be maybe even someone's job, this kind of stuff that we're showing here. And I can see how this could really make a big difference in terms of the cost that someone is going to incur, because they're going to use much less data. So let's go ahead and now create and query the views. So you can hide some of the complexity of queries from users by creating views. And because Athena only supports running one SQL statement at a time, you can use views to combine data from tables. And what we're going to do here is we're going to create 2 views to calculate the total for taxi fares that were paid with credit cards, and then total the number of ones that were paid with cash. So let's go ahead and first run this thing. So we'll go through here. Let's make another query. Paste this in here, and this will just create this view here that now we've got a view like this. And you can see, in fact, if I wanted to, I could even preview this thing. Right, I can see exactly what the view is. There we go. And then next, what I'm going to do is I'm going to create a view that looks at the cash trips here. So we'll create a second one, which is cash trips. Whoops. I think I didn't copy the create statement. There we go. So this is kind of the old days of being a database administrator. They're coming back now. But now you're a big data database administrator. So now what we can do is we can say select star from the credit card trips. So let's go through there, and we can do select star from credit card trips. And there we go. And then I'm going to do the second one, and I'm going to say select star from cash trips. And I can see the cash trips. Run the query, which I guess is similar to the preview. There we go. So you can then what we can do is we can do a view to join the data from the 2 tables. So before it was we could only get the credit card and cash as 2 separate queries. So we're going to create a view that selects this data together and joins it, and we call it vendor, and it's going to create this thing here. So we're going to go ahead and do this and create. I think I have to close this one. It's got too many open. Okay, there we go. Paste this in. So this is a giant SQL statement that basically says, I'll put the C in there. So it says create the view and put them together and call them vendor. And let's go ahead and run this query. And then now we have another, what do we call this thing? Compare pay. We have compare pay. And if I click on it, you see those 2. And if I go to the preview, it'll show me what's inside that new view. So I think I will be able to get you access to this lab, which is pretty cool. In that what's nice about it is that Athena could get really expensive to use it. And so this allows you to really experiment with something like Athena, and in theory be an expert at it before you play around and accidentally query a petabyte of data, and then your company gets really angry that you cost them a lot of money. But I guess the main takeaway with something like Athena here is that you can treat the S3 data, and let's even look at the S3 data. Let's actually look at the S3 data. You can just treat it like it's a database, which is really fascinating. And if I open this up, here we go. Here's our query taxi data, and you'll see what it is. It's just some flat files here. So it's text, right? And I think if I download it, it should show me some additional information about this. But it's definitely a pretty powerful mechanism to be able to use this lab. And again, I'll see if I can get you access to it. So that's the AWS lab here. So the next one that I'll show you, which I think is probably a little bit smoother, is we'll go through a quick lab one next. So I'm going to go to quick labs here. Quick labs. And hopefully you can still see my screen. Is that correct? Oh, you can't. Okay. So yeah, somehow kicked me out of there. So I'm going to share it again. Okay, so go to quick lab. There we go. So there are some really cool BigQuery ones inside of here, and the one that I've done the most is probably bike share. So it'll be the least bad at the bike share data set here. Bike share, BigQuery. Let's look at BigQuery. Let's see if I can find the one that I've done before. Exploring data sets. I believe that MySQL. So the one that I wanted to show you is a BigQuery, and I thought that they had it in the quick labs here, but if they don't, it's not a big deal. I can look. I can use another one of these things, but there is actually a pretty neat one that allows you to do like machine learning predictions. And let me just do one more search here just to make sure here. So BigQuery for machine learning. That's the one I wanted to do. Okay. There's a couple different ones that I've done before. So this is data analytics, baseline, chatbot. I think this could be, which one is this one? This is BigQuery e-commerce. To it. Okay, how do I get to that? So I would just say 281. Oh, like a would it be under catalog 281? Or maybe just throw me a link to it if you had one. BigQuery bikes predict. Well, I don't know what happened to this one. Maybe this one I think is a good one. This is close. So I've done this one too. So let me just grab this guy. So this is what also is neat about BigQuery that's a little different than the Athena is that you can actually predict machine learning right directly inside of this. So I'll throw this into our chat here. And what's kind of cool about this is that that it's no ops. You don't have to manage anything. Also, this is the one. So I accidentally got on the right one. So in this particular project, what we're going to do is we're going to start the lab. And what I like about this thing, this particular lab here, is that it lets us see the real power of these next generation big data systems. And so I'm going to go through here and maybe so if you want to follow along, just so I don't kind of fall all over myself this time, is I'm going to look at it in a separate window, and I gave you the link to it, and then I'm just going to walk through it so it's less clumsy. So I'm going to go through here, open up the window, and I'm going to log in and just kind of do it step by step. It's just a little bit clumsy to have to go back and forth, back and forth. Okay, so here we go. Here's password. Accept. Confirm. Okay, so I agree to the terms of service. So the big thing that it wants us to do at the very beginning here is that I'm going to go to the Bigquery Console. And so how do you get to the Bigquery Console? Is it's in the left here. And I think I can get to a bunch of different ways, but I can also just search for it and just type in Bigquery. And if you haven't had a chance yet to play around with Bigquery, of course, they have a new UI. One of the things to point out about it is that this whole this thing is pretty awesome in that I can go. We're not going to do it in this lab, but you can say explore public data sets, and you could go through here and grab like COVID data or grab whatever and just throw it inside of here and start easily querying it. But I'm going to be a nice citizen here and just follow along step by step with what the lab says. And so first thing that we're going to do is we're going to say welcome to BigQuery, and then the BigQuery console opens up, and then we're going to copy and paste this code into our query editor here. And so what's great about this is that because this data is publicly available right here, that I don't have to worry about like doing anything. Basically, it's built right in, and I can just immediately start running this against the publicly available data set. And in fact, I could just go like this, and I can start to see the data. Right, I can start to preview the data. Now, I don't know if this lab has access to it, but a lot of times I'll explore the data as well, and you can actually dump the data directly into this really cool data visualization studio called Data Studio, or put into Google Sheets, and you can actually start creating dashboards dynamically. So there are some tutorials that are outside of QuickLab. I don't know what exact queries are inside of or QuickLab demos that are exactly that do this, but when I'm using Google BigQuery, not inside of QuickLab, like my own account, this is primarily the kind of workflow that I like to do. Is I like to bring it into Data Studio to create dashboards and then share them with other people. Okay, so we got that completed, so that's good. The next thing that I'm going to do is I'm going to run a query here that will basically figure out the average speed of taxis. So let's go through here and let's just scroll down a little bit as well. Move this down so you can see this. I do a select and I go through and I figure out the round up the trip distance with the pickup drop off time, and again I query this publicly available table, which is a great way to not have to worry about data loading. And I say where the trip is greater than 0, and then I write some parameters in here, some and statements, and then I run this. And next up, we should see that these are the different speeds here that are available, right? And so we're able to see that the average speed is more like 11, 12 miles an hour. But we can see it. There's some different things that happen though that make things go like the hour, right? This is actually midnight, but at 5 a.m. you can see that this is actually 21 miles per hour taxi, showing that intuitively this makes sense that in New York City, well, actually right now in New York City, probably all the taxis are 21 miles an hour. They're probably all fast. but because there's less traffic on the road. Okay, so next step, what we're going to do is we're going to start to do some feature engineering, which would be really common. And maybe I'll just show you this in the other window so that this one doesn't seem too bad to kind of pop back and forth. But so now that we did this, this again would be a really common thing that you would do in a big data project or a project for a graduate data science program or something like that, is you would go to a public data set, or maybe it's your own proprietary data set, go through here, preview it, and start to, maybe tune the different things that you're going to use. And maybe one of the things that you want to do is you want to create a forecasting model. So you want to start to get to doing machine learning. And what's awesome is that the the BigQuery system, you don't even have to bring it into Python. You can just do machine learning right in here. So we can just start going right to the data science workflow, which is ingestion, which we already got covered, exploratory data analysis, which we just did, and then we're going to start to get into feature engineering and modeling. So next step here, what I'm going to do is I'm going to grab this data to kind of limit things a little bit and play around with it. So let's go through here and let's again replace this query. I'll move it down a little bit here and just throw this in. And there we go. So they wanted to tell me a couple things about this query that after I run it, I'll show those special things that they wanted us to know. You can also tell this is a kind of a beefy query here, but we see that it's got the passenger, it's got the hour of the day, the total fare that they spent. So and it also scanned 74 gigs of data. So it's doing a pretty big data set here. And so what do they want to tell us? They say a few things here is that the main query is select star from taxi trip, right? So that's the juice that's really grabs all the data. And then these other pieces are subsetting the data and doing where clauses and things like that. But the part that's tricky here is we're defining a variable called train, so we can build an independent evaluation set. And we should get something like this. And if we look at it, we did, right? So again, we have a pretty good proximity of that. Okay, so once we finish that, now what we're going to do is we're going to create a BigQuery data set to store the model. And so what we're going to do here is we're going to create a data set called, and for the data set ID, we're going to type in taxi, and then we're going to make the default location. So let's go ahead and do that. So we're going to say, in the left-hand resources here, select your project ID, which is this. And then we're going to say create data set. And for the data set ID, we'll call this taxi. And we're just going to leave everything default. And then we're going to say create data set. So now all this means is that we're now creating our own custom data set that is associated with our project, so that if I log into this project again, which I won't because it's Quick Labs, but I would get these things, basically access to these things. So we got that thing. Now what we're going to do is we're going to do our fancy BigQuery machine learning, which is actually one of the stealth features of BigQuery that nobody knows about. That's pretty awesome. Is that I can run all kinds of different models. I can do forecasting, so I can do numerical predictions. I can do binary and multi-class classification, or k-means clustering, and I can do it all in SQL, and I don't have to touch anything. So what are we going to do? Well, it's asking us which model type should you choose for predicting the taxi cab fare. The numeric, I would say it would be this one. Let's see if I'm correct. It says correct. So we want to do a linear regression here. And so if you look at this, basically it's going to say create a model called taxi fare model, and then inside of it we can define the machine learning algorithm, right? And we'll say we want to use linear regression. and we are going to have train and eval variables, and we're going to select these days of the week, and then these are just things that kind of select our data essentially. So let's go ahead and copy this and throw this into our query editor. So let's just go through here, and in theory, let's just double check I'm selecting the right thing here. So I'm on here. Yep, that looks good. And if I paste this in, just get this, copy it, and paste it. Okay, so let's double check that this looks good. So create a model, make sure it's a linear regression model. Okay, that looks good. Let's go ahead and run this. And what's awesome is I'm doing machine learning. I'm training a model, and I didn't even leave my Google BigQuery editor here. I was able to magically get this thing cooking. And I guess what it's doing right now is it's churning, and it will actually take about 5 or 10 minutes according to the documentation. So what we could do is just read through what's happening, give it 5 minutes or so. So what's going to happen as it's training, it's going to show up inside of this taxi location here. The model will actually be persisted. And then once the model is persisted, we can actually evaluate it against the data that we held out, right? The unseen evaluation data. So this is kind of cool in that what I like about something like this is that you're able to actually get right down to the weeds, and a lot of times you're optimizing for the wrong thing when you're dealing with Python. And maybe actually, let me just use this time. So I'm going to kind of time box myself for 5 minutes, and I'll come back and just show why I think this is kind of an interesting concept. I've been really looking into this concept of Kaizen lately. That is been around for a long time, but this concept of continuous improvement, right? And if you look at the word Kaizen, where did it come from? It actually came from something called the 5 whys. And so the 5 whys here. And why do I care about the 5 whys, and what does this even mean? Well, I think a lot of the machine learning that we're doing right now, people should be asking the question. And let me first explain the 5 whys, and then I'll explain how I think it could take place in the context of Python. So the idea would be that you can use it to get to the root cause of a problem. And in fact, this was originally created in terms of continuous improvement. And in fact, the creator of it was the founder of Toyota. And he was actually able to kind of make this whole evolution based on these 5 whys principle into Kaizen, which is now also part of lean manufacturing and Six Sigma. But it's a really an interesting question, which is, what are we doing? Why are we doing this? And you just keep kind of asking the question. So let me go through a fun why question here, just as an example. This is something I was dealing with recently. In fact, I was working with some people, and it was taking a long time to get something to done. And I actually was asking them. I was like, why is this taking so long? And I forgot even about 5 whys. I wasn't trying to be clever or anything. I was like, what there's got to be something going on here that's making things take so long. So okay, here we go. So here is the scenario of 5 whys. Is I was working on a project, and it turns out, like, why do I need to duplicate, and I apologize for the spelling, duplicate so much? Like, why am I putting the same data in the same location like 5 times? And then it turns out that, well, our system is broken. So basically their software system is broken. So I learned something just from the first question. It's like, oh, so I'm basically working around the fact that you didn't fix your system. Okay, well, why is your system broken? So why is it broken? And then it turns out that, well, we're busy. We're super busy. So their answer would be, oh, we're super busy. And then, well, what are you doing? Why are you so busy? Well, we're copying data all over the place, and so we're very busy copying data, and we can't get to fixing the system. And then hopefully then that starts to identify, like, hey, wait a second here, wait, this could take 2 days to fix. This takes an hour extra, and so what you're doing is you're basically never fixing something just because it takes a little bit of time to fix it, but you just added 40 days a year of problems because you weren't able to actually fix the root of the problem. And so this kind of concept is really actually a powerful concept for a lot of things we do. So now let's get into the most universities teach data science this way. Is they have like an academic data set, and they do all this stuff. And then I guess a question is why am I using Python? And again, I actually like Python, and I think there's nothing wrong with it for production machine learning. But let's just say, for example, why am I using Python for ML? Well, my teacher told me. So then, well, and then maybe you could dig into another thing. Is like, well, does this work with big data? With big data, and then the answer will be no, it doesn't. So regular Python, unless it's a PySpark or TensorFlow or something like that, it doesn't work. So it's like, well, why am I doing this? Why am I using a tool I can never use in the real world? This is a great, and I don't think many people have the answer for this. I can never use, because the question, probably their teacher told them, oh, just use this tool. But then they didn't go to the next step and say, but does this work with big data? No, it does not. So then you dig deeper and go, wait a second, why am I using something that I can't use in the real world? This is a vocational skill that I must learn. So not to like pick on this particular topic too much, but it kind of gets into what we're just seeing, which is, well, maybe the final step of this is, why don't I just use BigQuery? In the case of this example, I'm actually working on doing machine learning, and I instead of approaching the problem with a preconceived idea, I'm directly getting to the problem that I want to solve, which is I want to do machine learning. I don't care how I do it. And it turns out that the data set is big data. Like, for example, this would not work on your laptop, right? The 74 gigabytes of data will not work on your laptop. This will cause severe problems, and the default tools that you learn at a university or in Kaggle, they just won't work. Instead, you're going to need to use some other specialized tool. So why not just directly, in some cases, cut to the chase and build something directly that solves the problem. And this is just an example of something that potentially you could use as a form of process improvement. So we went through here and we found the model, and let's see what it says. So we did this. So and in fact, I guess I can show you too. It says go to model. If I click on this, that actually will show us a little bit of information about it. So it'll say here's how long it trained, and it'll show us the evaluation, so we can see what the error rate is, what the R squared is. So like all these things that you would typically find in some kind of a machine learning system, it's all giving you for free. And again, I never left the big data system, and I'm writing it in SQL. Okay, so let's go to the next part of our question here was, okay, let's evaluate the classification model, selecting your performance criteria. So for linear regression models, you want to use a loss metric like root mean squared error or RMSE. You want to keep training and improving the model until it has the lowest RMSE. In BQML, mean squared error, is a queryable field. When evaluating your trained ML model, add a SQRT to get a root mean squared error. Basically, we're going to change this so we can evaluate how the model performs by using ML evaluate. So we're just going to copy and paste this code, and we're going to run it. So we'll go to the next one. So we'll just say compose new query, and we'll go here and we'll paste this in, and we can see here it says mean squared error. So square root of mean squared error, right? Because that by definition, this is the root of square root of mean squared error. We're going to do evaluate. We're going to look at our model that was saved right here, and we're going to go through and evaluate the accuracy of it. So let's go ahead and run this. And I think this will be pretty quick, and we can see that the root mean squared error is 9.4. And if we go back to this, it's the same thing. So after evaluating your model, you get a root mean squared error of 9.47. So what this means is it's in the same unit. So basically, we have plus or minus $9 total fare error, and so knowing whether or not this loss metric is acceptable to productionalize or operationalize your model is entirely dependent on the benchmark criteria, and so we would need to evaluate that based on what our company would want us to look for. So what we're going to do now that we've got this is we're going to predict a taxi fare amount. Now we've got a pre-trained model to a location. So we're going to copy this data, and you can see here that this actually feels pretty useful. Like, just imagine when you cut to the chase like this, how quickly you could start building machine learning models that solve real problems. So in this case, now that we've evaluated it, we know what our trade-offs are for our model. We can go through and just do some predictions. And in fact, what we can look at here is we can see what we think the predicted fare would be. For each location inside of our data set here, and I think it also will show us, if I scroll over here, yeah, the passengers as well. So like it'll use that as a parameter here. So now that we're able to predict things, you can actually see the actual fares versus the predicted fares. So that's predicted. So let's go through and let's improve the model with feature engineering. So we know again that when you're training a machine learning model, a big part of the problem is that it's very unusual for you to just pick the right features at the very beginning and then things just work magically. You're going to have to do some magic to get this thing to work. So what we're going to do is we're going to view the statistics, so like the descriptive statistics, right? But we're going to use SQL to do descriptive statistics. So this is oftentimes, right, a process of exploratory data analysis is, hey, let's look at the features of the data to see if we can find something neat here. So we'll go through and we'll do that. And if I paste this in, this will show us hopefully some interesting information. And so we can see here what the high fare is, what the low fare is, the number of fares, the average fare, and also the standard deviation is actually, that looks fairly ridiculous of a standard deviation for the taxi data. So I haven't read the rest of it. My guess would be there's some really bad data in this data set here. So let's look through. So they're saying that, yeah, you can see that there's some strange outliers. So okay, they're thinking the same thing that I'm thinking, which is, wait a second here, we have negative data and we have fares over 50,000. Come on, how often is that really going to be happening? So let's actually apply some of the subject matter expertise and just limit the data to like something that's reasonable. Maybe we don't really care about $50,000 prediction. I mean, maybe that's true, that maybe there are these really rich people that do this, but more than likely something like, the average fare is going to be closer to the range in there. So let's go ahead and select this, and we're just going to limit the fare amount between 6 and 200. So again, because SQL is so awesome to work with, what we can do is we can just go through here and just kind of limit things, then do descriptive statistics, and then all of a sudden, now our standard deviation looks like, okay, this feels more normal. We had some really wacky standard deviation here, but this feels like, look at how many fares we're comparing, and we're actually able to get a pretty nice distribution of data, right? Average fare, standard deviation, right? So this looks like this could make a huge improvement in the accuracy. And then let's also limit the distance so we're really on New York City as well. So what this is going to do is they're going to limit the data to, I'm assuming they must know the latitude and longitude of New York City proper, which I don't know, but they do. I'm going to go through and I'm going to make a new one, and I'm going to limit the data here. And here we go. We're able to limit this data even further, right? So we get the same descriptive statistics, and it looks like I don't know if that really helped us that much or not, but let me just double check here. So yeah, the standard deviation, did it really help us? Only a little bit. It's very, very minor change here, because the average went from 12.9 to 12. Yeah, it's very minor. So we still have a pretty large training set. So if 800 million rides, just by getting rid of that, we're able to massively change the accuracy of the model by cleaning up the data. And so to retrain the model, what we'll do is create a new model called taxi fare model 2, retrain it linear regression, but we're also going to add a calculated feature called Euclidean distance between the pickup and the drop-off point. So Euclidean distance really is just, in multi-dimensional space, what's the shortest distance. So let's go ahead and copy this, paste this in, go to new query, and let's just look at this query real quick here. So we've got, that makes sense. So replace them, make a new model, do the same things we did before, and then also generate the Euclidean distance here, which is right here. Okay, so yeah, by the way, the Euclidean distance is a pretty simple equation, so it's not that tricky to generate. And we're going to go through here and run this. Now, I think again, this one will take. Let me just look at what they say it'll take. I think it's probably going to take like 5 minutes. Actually, maybe it's much smaller, which is interesting. So it'll take a couple minutes to retrain the model, which is interesting. I'd be curious why that might be an interesting thing to figure out. Is why would this only take 2 minutes? Um, but let's just let this thing crank for a little bit here. So it's on 60 seconds. But to me, what I like about these kind of BigQuery machine learning demos that they show you is that the stuff that I personally care about with machine learning is I want to train a model, I want to save it, I want to compare things, is I get to work on the stuff that's fun instead of the stuff that's not fun. And this definitely goes right to the fun part. So now that I've got this second model, I'm going to evaluate it, doing the same thing we did before. So again, go through here, paste this in, and we will just say evaluate this model, but this time use the new one I created. Perfect. Root mean squared error is this. And next up here, we will see that this root mean squared error is much lower, right? The other one was 9, and this one is 5. And so we've actually got we went from 9.47 difference to plus or minus $5. And so a lower root mean squared error indicates a more accurate model that is correct. And so if we want to, we can use the following link to look at other taxi data sets. But I think what we could do here, actually, if I want to do one more prediction, I can, hopefully I don't get in trouble by doing this with Google BigQuery, but I think before we did a prediction, so I'm just curious what a prediction would look like if we did it on the new model. So I'm going to go ahead and select this, predict taxi fare amounts, and then I'm going to go to this system here, paste this in, or make a new query, paste this in here. And I think I would only need to, wait, let me grab this. I'm going to copy this, and I'm going to go back to this. So this is the old one. I believe I can just go here and just say taxi fare model and then put _2, right? And then this should, in theory, I don't know why that's angry. Predict column is not found. Well, anyway, without doing live coding on weird SQL that someone else wrote, I think the big takeaway here is that when you use something like BigQuery, it really does allow you to go back into this 5 whys kind of scenario where I think this, I guess, is maybe the way to wrap up what we're talking about, is that why am I using the cloud? Like, what is the problem that it's solving? And I think what we're seeing here in terms of the cloud is that it really does allow you to kind of focus on I guess that Kaizen concept here, which is like the question is, am I getting better? And then in the case of the cloud, I think you really can say on a daily basis, you can say, yes, I'm getting more more efficiency. What I'm doing is I'm focusing on the problem that I care about, which is that I want to do a prediction and I want to compare and create like accuracy on the models, and then I want to basically deploy this into production. And so I think these are the things that are important to think about in terms of this Kaizen feedback loop here is when you're using these big data systems is, do you need the complexity of Python? In some cases you do, in other cases you don't. And if you're just going to deploy some kind of a machine learning model, maybe it's better to focus on a system like BigQuery or an equivalent system where it's doing all of the work for you, and it's able to actually give you a lot of enhanced capabilities that it would be impossible for you to build yourself. So I think that's probably the biggest takeaway from these cloud-based platforms is it allows you to just focus on the stuff that's important, get rid of the stuff that's not important, and that's basically why I think they're so important.